Good day, everyone. The question assigned to me is, write down the expression for the radial distribution function of a 3p electron in a hydrogenic atom of atomic number Z, and determine the radius at which the electron is most likely to be found. So in order to solve this problem, the equation or the formula that we'll be using is this one. P times the function is equal to r squared times capital R times the function squared. And this equation is what is known as the radial distribution function. And this capital R times the function squared is what is known as the radial wave function, which depends on the quantum numbers n and L. So we can rewrite, based from the problem, we can rewrite this equation as P sub 3p, because we're looking for the 3p orbital, is equal to r squared times r sub n and L. And n in this case is equal to 3, as given here in the problem, and L is equal to 1 because we're looking at the p orbital. If it is the s orbital, L is equal to 0. If it is the d orbital, L is equal to 2. And if it's the f orbital, L is equal to 3. So this function R sub n and L can actually be found in this table, which is known as the hydrogenic radial wave function. So once again, we take a look at the quantum numbers n and L. So because n is equal to 3, we have these three options. However, our L is equal to 1 because once again, we're looking for the p orbital, therefore L is equal to 1. So we have this function that we'll be substituting towards here. But to make it easier to solve, we will make this a constant. So after substituting it over here, we will get r squared times a constant, which is this one, times 4 minus rho times e to the power of negative rho over 2. And this entire function is squared as seen from here. After distributing the squared, you will end up with r squared times c squared with the constant squared, 4 minus rho squared, and e to the power negative p, since the 2 will just cancel out. Now, at this point, we can simplify the function by expressing it in terms of either r or rho. So because majority of them are in rho, therefore I let r squared be equal to rho squared. So substituting with r squared to rho squared, we will get this equation. Now rho here actually can be expanded, which is equal to 2 zr over n times alpha sub 0, where z here is the atomic number, r is the radius, n is the quantum number, and alpha sub 0 is the Bohr radius. So because we know n is equal to 3, so therefore we substitute n with 3. However, we will not substitute rho with this yet, so it will be easier for us to solve in finding the r. But we will be using this equation later on, towards the end of the solving. So to find the most likely radius, we can set the derivative of the p3p orbital equal to 0. Therefore, we can collect all the multiplicative constants together, since they will eventually be divided into 0. And there's an important note. So note that not all the extrema of p are maxima, while some are minima. But all the extrema of the p3p raised to 1/2 correspond to maxima of the p sub 3p. So let us find the extrema of the p sub 3p raised to 1/2. So because we are finding for the extrema of the p sub 3p raised to 1/2, or basically the square root, we'll get the square root of both sides of the equation. So the square here will just cancel out, the square root and squared, all the squares will get cancelled out, and negative rho will become negative rho over 2. Therefore, we'll get this. And then we'll combine the like terms here. So rho times rho, you will get rho squared. So the constant times rho squared times 4 minus p times e raised to negative rho over 2. And I'm sorry, but this should also be squared. So as I mentioned earlier, we set the derivative of the p sub 3p raised to 1 half equal to 0, so that we can collect all the multiplicative constants together, since they will eventually be divided into 0. So equals to 0 is equal, we get the derivative of this function, and we'll end up with, since it's a constant, we just leave it outside. So the constant times rho times 8 minus 5 rho plus rho squared over 2 times e raised to negative rho over 2. So we divide this entire equation by c times rho times e raised to negative rho over 2, and we'll end up with 0 is equal to 8 minus 5 rho plus b squared sub 2. So this equation looks very familiar, and it is almost in the form of the quadratic formula, which is ax squared plus bx plus c is equal to 0. However, there's still a 2 here, so we times both sides by 2, since 2 times 0 is just 0, and the 2 here will cancel out, and 8 times 2 is 16, minus 10, 5 times 2 is negative 10, plus rho squared. And just rearranging the formula to the ax squared plus bx plus c, you'll end up with this. So now that we have this, we know that a is equal to 1, b is equal to negative 10, and c is equal to 16. So using the quadratic formula, substitute the values here, and obviously we'll get two answers. So rho is equal to 2 and 8. So earlier in the video, we said that rho is equal to 2 zr over 3 times alpha sub 0. So because we are solving for r, we're solving for the radius, we isolate r to one side, and we'll end up with 3 times alpha sub 0 times rho all over 2z. And since we calculated for rho earlier, which is 2 and 8, we just substitute rho with 2 and with 8, and we'll come up with two answers. So r is equal to 3 times alpha sub 0 over z, and r is equal to 12 times alpha sub 0 over z. Now PR is larger at the 12 Bohr radius than at the 3 Bohr radius. So the most probable position of finding the electron of a 3p orbital is at the radius equal to 12 alpha sub 0 over z. And here's a summary of this problem. Thank you so much for watching.